Hello, and welcome to the Hardware, Introduction, and Visual Troubleshooting presentation. This is Session 1 of the Programmable Logic Controllers, PLC, ControlLogix Fundamentals, and Troubleshooting series. This presentation is brought to you by Flux Automation, LLC, and the Non-Ferrous Founders Society. In this series, we will discuss the fundamentals of PLCs using the Allen Bradley ControlLogix platform for our demonstrations. These brief sessions are intended for entry-level individuals that may be intimidated or interested in PLCs and/or automation. Our goal is to provide basic knowledge and break down these systems into simple, easy-to-understand segments to wane fears. First, a little about myself and Flux Automation. My name is Dan Horvath. I will be your presenter for today and the remainder of this series. I have over 20 years of controls and automation experience in various industries and several years of foundry experience. Flux Automation Services provides a complete list of automation and integration services, including but not limited to PLC programming services, control panel design and fabrication, control system upgrades, industrial servers and networking, system assessments, anytime emergency services, and control system consulting and consultation. For a complete list of our services, please visit our website at www.fluxautomation.com. Flux Automation aims to simplify technical information to educate industrial clients about their control systems, fostering their comfort and understanding. The information provided in this session is intended for reference purposes only. Agenda. During today's session, we will be covering the following topics. What is a PLC? A brief history of the PLC, a ControlLogix hardware overview, chassis overview, PLC processor overview, overview of a couple I/O modules, visual troubleshooting and status indicators, and then following this up with a live question and answer session. This presentation has been pre-recorded, so please save your questions to the live Q&A section at the end. What is a PLC? A programmable logic controller, or PLC, is a specialized computer-based device used in industrial automation systems to control and monitor processes. It is designed to withstand harsh industrial environments and is widely employed in various industries such as manufacturing, energy, chemical, and automotive. The primary function of a PLC is to automate and control the operation of machinery or processes. It receives inputs from sensors and other devices, processes the information using programmed logic, and generates outputs to control actuators, motors, valves, and other devices. PLCs are highly versatile and programmable, allowing engineers and technicians to create customized control strategies for their intended applications. The programming is typically done using ladder logic, a graphical programming language resembling electrical circuit diagrams. However, modern PLCs also support other programming languages such as function block diagrams, structured text, and sequential function charts. PLCs offer numerous advantages in industrial automation. They provide reliable and real-time control, enabling precise and accurate operation. They are capable of performing complex logic operations, timing sequences, arithmetic calculations, and data processing. PLCs also facilitate easy integration with other systems, such as human-machine interfaces, HMIs, or supervisory control and data acquisition, SCADA, as well as integration with enterprise-level networks. Furthermore, PLCs have built-in diagnostics and monitoring capabilities, allowing for efficient troubleshooting and maintenance. They can store and log data, generate alarms and notifications, and provide remote access for monitoring and control purposes. This makes PLCs invaluable tools for improving productivity, safety, and efficiencies in industrial processes. Overall, PLCs play a critical role in industrial automation, providing robust and flexible control solutions for a wide range of applications. A brief history of the PLC. The concept of the PLC emerged in the late 1960s and early 1970s as a response to the need for a flexible and reprogrammable control system in the manufacturing industry. Before PLCs, control systems relied heavily on hardwired relay circuits and large control panels, which were difficult to modify, troubleshoot, and maintain. In 1968, engineers from General Motors developed the first programmable logic controller called the Modicon, which stands for Modular Digital Controller. It was designed to replace hardwired relay systems used in automotive manufacturing plants. The Modicon PLC introduced the idea of using solid-state electronic components and digital logic to control industrial processes. The original Modicon PLCs used a simple programming language known as ladder logic, which resembled electrical circuit diagrams used by electricians. This made it easy for electricians and technicians to understand and program the controllers. In the following years, other companies such as Allen Bradley and Siemens also entered the PLC market, furthering advances in technologies. PLCs evolved to include more advanced functions such as analog control, communication capabilities, and increased processing power. Throughout the 1980s and 1990s, PLCs became widely adopted in various industries, revolutionizing industrial automation. They offered significant advantages over traditional control systems, including easier programming, greater flexibility, and improved reliability with reduced downtime. With the advancement of technology, PLCs continued to evolve. They became more powerful, compact, and capable of integrating with other systems such as HMIs, SCADA, and industrial networks. The introduction of advanced programming languages, increased memory capacity, and faster processing speeds further enhanced their capabilities. In recent years, PLCs have embraced concepts from the Industrial Internet of Things, IIoT, and Industry 4.0. PLCs now feature connectivity options, cloud integration, data analysis, and remote monitoring capabilities. This enables more advanced automation, predictive maintenance, and optimized for industrial processes. Today, PLCs remain a vital component to industrial automation systems, facilitating precise control, data collection, and analysis in various industries worldwide. They continue to evolve alongside emerging technologies, playing a critical role in the ongoing digital transformation of manufacturing and industrial sectors. ControlLogix Overview. We will be focusing on the ControlLogix family of PLCs, also referred to as PAC, Programmable Automation Controllers, in this session. ControlLogix is a family of programmable logic controllers manufactured by Rockwell Automation. It is part of the Allen Bradley product line and is widely used in industrial automation applications. ControlLogix PLCs are known for their modular design, scalability, providing flexibility to meet the needs of various control system architectures. They are designed to handle complex control tasks, large input and output capabilities, and high-performance applications. ControlLogix PLCs utilize a common control engine and programming environment called RSLogix 5000, and now known as Studio 5000. This software allows engineers and technicians to program the controllers using a variety of programming languages, including ladder logic, structured text, function block diagrams, and sequential function charts. In this series, we will be focusing on ladder logic. The ControlLogix platform offers a wide range of modules, including CPU modules, input and output modules, communication modules, and specialty modules. These modules can be easily added or removed to accommodate the specific requirements of an application. The system can support a large number of I/O points, allowing for control of extensive industrial processes. ControlLogix PLCs provide advanced features such as built-in diagnostics, redundancy options for high availability, integrated motion control capabilities, and extensive communication capabilities. They can seamlessly integrate with various industrial networks and protocols, enabling connectivity with other devices and systems in the automation infrastructure. Additionally, ControlLogix PLCs are designed to support distributed control architectures. This means that multiple controllers can work together in a coordinated manner, sharing information and distributing the workload. This is beneficial for complex automation systems. Overall, ControlLogix PLCs are known for their robustness, flexibility, and scalability. They are widely used in industries such as manufacturing, oil and gas, power generation, and others, where precise control, extensive I/O capabilities, and high-performance automation is required. Next, we will be taking a look at a ControlLogix chassis. For demonstration purposes, we will be using a 10-slot chassis, also known as a ControlLogix rack. Alright, here is a ControlLogix chassis. As you can see, this is a 10-slot chassis, starting with slot 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here on the label, you see the catalog number 1756 indicates the ControlLogix family of devices. A10 indicates 10-slot chassis. The backplane in the chassis, that green circuit board, serves as the communication pathway between each module on the chassis. So to get started, we'll add the power supply to the ControlLogix chassis. So ControlLogix power supply, this is 120 volt power supply. You can see the on-off switch and the power connection right here. So essentially what the power supply does is slides onto the end of the chassis. Slides all the way down, snaps into place, and then there's two Phillips head screws that will screw down to mount the power supply to the chassis. This chassis is typically mounted onto the backplane of a control panel. Mount it on the wall like such. There's vent holes in the top for heat dissipation, but for demonstration purposes, we're just going to lay it here on the workbench. Now that we have our power supply attached to the chassis, go ahead and turn power on. You'll notice a green LED light up to indicate power is on. Now this chassis is ready for I/O modules. Next, we'll be talking about the PLC processor. The PLC processor is the brains of the operation. This module executes all the logic code and controls all the I/O, communications, and specialty modules assigned to it. This is a PLC processor, PAC, as mentioned in the presentation. Again, we have 1756, L for Logix, and 63. The 6 represents the generation of processor. Currently, Allen Bradley offers a 7 series and 8 series. For demonstration purposes, we're just going to stick with this older 6 series processor. And then the 3 represents memory size. So you have a 1, 2, 3, 4, and that's typically represents the amount of memory that the processor's built with. In the front of the processor, you have a key switch, which we'll get into more details later. A little door. Behind the door, you have a RS-232 communication port, a battery. This battery is used to hold to flash the program to non-volatile memory during power failure. It's very critical. We'll discuss that further later in the presentation. We also have a compact flash memory card, which will store a version of the processor and can be retrieved during power up. So you can see there's a series of small pins on the back of this processor, and that has to line up with the female end and the chassis. It's very important to slide these cards in straight so none of these pins get bent. So to simply do this, we'll start with slot 0, slide it in the groove here, and straight down. Now I am doing this with the power on. You can rack in and rack out these cards with the power on. We'll see the processor boot up. So we have a green OK light. That means it's passed all of its internal checks. Run light, which means that the program is currently running. And an I/O light is flashing because What's configured here in this processor does not represent what's actually in the chassis currently. The next module we will be installing in the chassis is a network module. This particular module is an Ethernet communication module. This allows the PLC processor to communicate to other I/O racks, human-machine interfaces, SCADA systems, and other networked devices. This module is a 1756 ENBT, Ethernet Communication Bridge Module. Communicates via Allen-Bradley Ethernet IP industrial protocol at speeds of 10, 100 megabits per second. This is an older communication module, but it's good for demonstration purposes. On the bottom, there is one RJ45 port for standard Ethernet connection. On the front, a couple of status LEDs and the display. Just as before with the processor module, we'll insert this card into slot 1, straight down, push until it clicks. The Ethernet module will perform a self-test, then display the current configured IP address. Standard Ethernet cable plugged into a switch. Now the module will have a link light. When a HMI or device is connected to the module, this net light will turn green. The next module is a standard 10 to 31 volt DC input module, 1756 IB16. Again, 1756 designates the ControlLogix family. I for input module. B designates a DC module. A typically designates an AC module. And 16 designates the number of inputs. As you can see by the circuit diagram, this is a sourcing input module where positive DC voltage must be applied to the input for the signal to be high or true. This module is broken into 4 different groups. Each individual groups must be supplied a negative DC common in order for that group of inputs to function properly. Just as we have done with the past 2 modules, we will slide this module into slot 2. In order to wire to these modules, there are these removable terminal blocks. They are usually referred to as RTBs. The cover will slide off like so. You have your individual screw terminals, allowing your wire cabling to come in from the bottom and terminate to the module. These RTBs snap onto the front of the module, straight down, and then will lock into place. On the front of this module, there are status indicators indicating when an input is high or on. Since we don't have anything wired to this module currently, there will be no status indicators. The final module we will be covering today is a 10 to 31 volt output module, 1756 OB16E. The O designates an output module, B designates a DC module, whereas a W will typically designate a dry contact output module. 16 designates the number of output points, and finally E designates electronically fused. This is a low current output module to drive devices such as solenoid valves, relays, indicator lamps, etc. As you can see in the circuit diagram, this is a sourcing output module. The module is broken down into 2 groups. Each group requires a DC positive and DC negative connection to function correctly. Here is our final module for today. As you can see, I've already installed the removable terminal block. So once again, I'll slide this module into slot 3. Now, an interesting thing to note, now that I have my two I/O modules in place, my I/O OK light has gone solid green. These two modules were configured in the project prior to this demonstration. So now that all the proper modules are in place, the I/O light has turned solid green. You can also see on the output module, I programmed a little sequencer to flag each one of the outputs. For the final topic in today's presentation, we will be discussing visual troubleshooting of the status indicators. We will be discussing an overview of the status LED indicators on displays, overview of the PLC processor key switch functionality, how to check for loose modules and wires, and basic troubleshooting. Use your senses. When troubleshooting your PLC system, the first thing to look at are the status indicators. There is a lot of information that can be obtained from looking at these LED lights. First of all, on the processor, you have several LED lights here. The first one is the run light. This means that the PLC processor is in run mode and is processing logic. The second is the I/O light. This is a great indicator of your I/O status. If the I/O light is blinking, that means that the processor cannot communicate to some of its I/O cards. That may be within this local rack. It also may be within a remote rack. Next is this forced light. This indicates that an I/O point has been forced on or off within the program. RS-232 light just indicates communication over the RS-232 port. The battery light, if this is ever red, this means that the battery within the PLC processor is dead. When this happens, if power is lost, the program within the PLC processor will be lost. Finally, this OK light. If this is never not green, that means there's a hardware issue with the PLC processor. Next on this Ethernet card, we have the link light, which means it has an active communication link to the rest of the network. Like I mentioned before, this net light, when this is solid green, is communicating to an HMI or other device. OK light also indicates that we have a hardware issue. All your I/O modules will have an OK light as well. When diagnosing a problem with the program, the input lights will tell you which inputs are high. The output lights will actually tell you which inputs the program is driving high. If for some reason there is an output that is on, but you're not getting an active solenoid, relay, or etc., then there may be an issue with the device connection. Next, let's talk about the PLC processor key. This key puts the processor into 3 different modes. First mode is in the middle. It's remote. This allows a programmer to connect to the processor and make program edits. The second is run. This will run your project, but will not allow somebody to connect and make edits. Third is program. When the processor is put into program, your run light will turn off. This means code is no longer being executed and all outputs will be turned to a fail-safe manner, designated by the program. If for some reason you ever find your PLC processor in this state with not a run light, you can simply turn the key over to run and the program will start up again. You want to make sure you visually check that all of your PLC cards are seated within the rack. Make sure that all the wiring is tight and neatly organized. Also check the top of the rack to make sure there is no debris or metal shavings. Proper ventilation and heat is concerned. If there is excess heat, it will cause card faults and issues. Upcoming sessions in this series. In this session, we covered hardware introduction and visual troubleshooting. The next session, 2, connecting to your PLC and I/O module setup. In this session, we'll be using RSLogix 5000 to create a new project, connect to the PLC, and configure the I/O modules within the project. In session 3, We will be configuring a program routine and discussing memory configuration, types, and allocation. In session 4, we will be covering basic logic instructions and writing a simple ladder logic program. Finally, in session 5, we will be discussing logic troubleshooting methods. On the behalf of Flex Automation and the Non-Ferrous Founders Society, we would like to say thank you for your time and interest in our presentation. Please don't hesitate to reach out to us for further information. This has concluded the recorded section of this presentation, and we will now conclude with any questions you may have. Thank you.